Welcome back to another video. Today is going to be all about heat transfer, which is a topic that you'll find in both physics and chemistry courses. I'm going to look at it more from a physics lens, but the concepts are always applicable to either course. All right, so we know, what heat is. As something gets heated up, it gets hotter. But what that actually means is we are giving a substance or an object more energy. And the amount of energy that we need to add to an object or substance to increase its temperature is dependent on what's called heat capacity. So everything in the universe has its own unique heat capacity. And I have two written out for us right here. The first one is for water. And this is specifically water in liquid form. So when we have liquid water, we need to add 4.184 joules of energy to heat up 1 gram of it by 1 degree Celsius. And that's what the values here represent when we talk about heat capacity. So it's joules per gram Celsius. Once again, this is the amount of energy to increase the temperature of 1 gram of water by 1 degree Celsius. If we compare that to copper, we can see that it's much, much lower, which makes sense. Metals tend to get hot very, very fast compared to water, and that's because they require a lot less energy inputted to see this temperature change occur. And what we can do with these heat capacity values is use this equation down here to actually calculate the total amount of energy that is required to raise the temperature of a certain object depending on its mass. And let's get a quick example done here. Let's imagine I have 100 grams of water. Once again, liquid form. And we know the heat capacity of water. Let's say the water starts at 10 degrees Celsius, but I want to increase its temperature all the way to 40 degrees. So the way I'm going to input all of these values into this equation is I have my mass, which is 100 grams. I have my heat capacity for liquid water, which is 4.184. And I have my temperature change, which is represented by delta T. And for temperature change, we want to subtract our initial temperature from our final temperature. So our final value was a 40, our initial was a 10. That means that we're going to have a temperature change of 30 degrees. So let me just quickly write that out here. And when I plug in all these values, I get around 12,500 joules of energy. So this is how much energy is required to raise the temperature of 100 grams of water by 30 degrees. Now what we can do with this information is we can actually pair it with the first law of thermodynamics. We know that energy cannot be created or destroyed, which means that the energy gained by one substance must have been lost by another. So in our previous example, the 12,500 joules of energy that was added to the water has to have come from something else, right? We can't just create energy out of thin air. It needs to have been transferred from another system or another substance. What that means is, if we were to take the energy lost and add that to the energy gained, we should get a net value of 0. And so this setup here that represents the first law of thermodynamics is super useful when trying to solve these heat transfer questions. And let's use this one down here to highlight this. So a 0.3 kilo piece of copper, initially at 80 degrees Celsius, is submerged in 0.2 kilos of water. If the water initially has a temperature of 20 degrees Celsius, what is the final temperature of the system? Now, what I'm going to do is I'm going to think of this as energy lost plus energy gained has to equal 0, meaning the energy lost by the copper when it's placed into the colder water is the energy gained by that same water to raise its temperature. What this means is we can actually set up two instances of our other equation, which was mc delta T, and we can set this to 0. So this here is the energy lost by the copper, and this will be the energy gained by the water. Looking at copper, we're given its mass in kilos, but I'm going to turn that into grams because earlier we were looking at heat capacity in joules per gram Celsius. So let's keep things consistent. The mass will be 300. The C value, I believe, was 0.385. And then for our temperature change, we don't know what the final temperature of copper is, but we were given its initial temperature. So I'm going to leave final temperature as a variable, and I'm going to subtract that from 80. And now I just need to do the same setup for water. So I have 200 grams of water. The heat capacity should be 4.184. And again, I don't know what the final temperature of the water is going to be, but it did start at 20 degrees Celsius. And this whole thing is equal to 0. So this is going to be enough to solve for this final temperature because we're looking for the final temperature of the system, which insinuates that at the end of all of this, the copper and the water are going to reach the same temperature once all of the energy transfer has been completed. So what we really need to do is just now solve for this missing variable. If we plug these values in, this is what we're going to end up with. And at this point, it'll be pretty straightforward to solve. We just need to remember to use the distributive property on our brackets, which will give us these values. So 115.5 times 80 is 9,240. And over here, we have 836.8 times 20, which is 16,736. So now we just need to make sure we have our variable on one side and our constants on the other side. So if I were to move this number and this number over my equal sign to the right, that would give me a value of 25,976. And then if I collected my like terms here with my variable, that's going to leave me with 952.3. And then to solve for our variable, we just need to divide out this value. So our final temperature for the system is roughly 27 degrees Celsius. And that honestly covers the basics of heat transfer questions, but there is going to be one other concept that could complicate things. So let's take a look at what that could be. When we add energy to a system, it doesn't always lead to an increase in temperature. It could actually cause the change in a substance's state of matter. And usually to represent this, you're going to be shown a graph like this. So this is just showing the energy added on our x-axis with the temperature change in a system on our y-axis. And in this example, we're going to be showing the energy added to an amount of water. So we're starting way down here. And let's say this is like minus 30 degrees Celsius because we are in the ice form or the solid state of matter. And as we add energy to the system, we can see the temperature steadily increasing. But then when we reach a certain temperature, let's say this is 0 degrees, we can see that our slope kind of flatlines. And this is because what's happening here is our ice is turning into liquid water. So at this point, the temperature of the ice/water is not changing, but its state of matter is changing. And that's what the energy is doing. And that's just what I wrote here. When water is changing state, its temperature remains constant, but it still gains energy. This is what drives the change to occur. And this energy is known as latent heat. So whenever you hear the words latent heat, that's referring to the energy that's causing a state change for a substance. What we can see continuing on our graph here is eventually all of our ice turns into liquid water. So once we add more energy beyond that, the temperature starts to rise again. Then, as we're getting up to about 100 degrees Celsius, we reach another plateau, which is another area of latent heat, where our liquid water is going to be turning into vapor. Therefore, the energy added here doesn't increase our temperature, it just causes the state of matter change. And then finally, we continue to increase our temperature as we are now in the vapor form of water. So down here, you'll see the variable LF, and that refers to the latent heat of fusion. And fusion is the term we use when we're describing going from a solid to a liquid. And then up here, we have the latent heat of vaporization. Honestly, I don't even know if vaporization has an S or a Z, but let's use a Z. This is pretty straightforward. This is when we're turning from a liquid to a vapor or gas, hence the name. But both of these values, LF and LV, are going to have values associated with them. For example, when we're talking about going from solid ice to liquid water, the latent heat of fusion has a value of 330,000 joules per kilogram. So you can see this is quite a lot of energy to change a kilo of ice into liquid form. And usually when you're asked to solve for the amount of energy required for this change in the state of matter, you're going to be given this value of latent heat of fusion or vaporization. And the way we solve this is we take our latent heat value and we're just going to multiply it by the mass of whatever object or substance we have. Let's apply this to an actual question. What is the total amount of energy required to heat 150 grams of ice from a temperature of minus 20 degrees Celsius to a temperature of 50 degrees Celsius? So we're not really worried about seeing where energy was lost and gained. We're only concerned about how much energy needs to be inputted into this system to cause this complete temperature change. If we think about what's happening here, we're going from minus 20 degrees Celsius ice up to 0 degrees, and that is when it will start to melt. Then we're adding energy for the latent heat of fusion. And then beyond that, we're adding energy to go from 0 degrees Celsius in our liquid form up to 50 degrees Celsius. And I'm actually going to represent all three of these steps in an equation. MC delta T is going to represent my ice warming up. Then I need to consider the energy for the state of matter change. And we just looked at an equation for that, which is mass times our latent heat. And we're going from solid to liquid, so this will be a fusion value. So this is our state change. And then finally, one more MC delta T to represent our water warming up. We have all of the necessary information on the right here, but since the latent heat of fusion for ice refers to mass in kilograms, I'm actually going to change the heat capacity for ice and water into kilograms as well. And that's pretty straightforward, because if it takes 2.03 joules to heat up 1 gram of water, it would take 1,000 times more energy to heat up a kilo. So we just need to move our decimal places 3 spots here to change from grams to kilograms. What you also may have noticed here is you cannot use the 4.184 value for water in all of its forms. If we're dealing with ice, if we're dealing with vapor, they are going to have their own unique heat capacities. But anyways, let's carry on. We've got all the information we need. We just need to plug our values into our equation. And I guess this entire thing could be set to Q. Q just represents energy in general. Let's start plugging in our values. We are working in kilos, so I want to say we have 0.15 kilos instead of 150 grams. The heat capacity for ice will be 2030. And our temperature change will be a value of 20, but I'll show that with our final and our initial value. And the mass will be the same in all 3 spots because we're dealing with just 1 mass of water. And this is a very high value. And then here, our final temperature is 50. We started at 0. That's going to be a change of 50. So I can turn this into a positive because 2 negatives cancel out. So this will just be a positive change of 20 degrees. And plugging in all of these values into my calculator, I'm going to get 6,090 plus 49,950 plus 31,880. And so this is our energy for the ice warming up, energy for the state change, and finally energy to warm up our liquid water. And you can see that the energy for the state change actually eclipses both of our MC delta T equations. So energy for latent heat is quite large compared to just heating something up in terms of its temperature. And finally, let's add all these values together, and we get roughly 87,000 joules of energy. And that is pretty much it. So questions are going to basically just remix these 2 ideas that we went over. You might be solving for the amount of mass that you started with. You might be solving for initial temperature instead of final temperature. So they'll find things to change up. but that pretty much covers the gist of it. Hopefully you found this useful. Thank you very much for watching, and good luck studying.